our next theorem will be theorem 253. Where we prove that there are infinitely many primes. So that's our statement P. So we argue by contradiction and we write not P. So what's not P? There aren't infinitely many, there are finitely many primes. And now from that assumption, we want to reach the contradiction. So here it is. If there are finitely many primes, we can write a list of all the primes. So list of all the primes. What are those? P1, comma P2, P2E, and there is last one, Pk. No more, every prime is here. If there are finitely many, we can just drag them all down, right? It might be a long list, doesn't matter, there is a finite list. List of all the primes. There are no primes outside of that list. And then what do? We make a huge number. We call it A, doesn't matter, it's the same. A equals. And we multiply all these numbers. P1, P2, P3, Pk, plus 1. So it would be an enormously big number, but theoretically we can do that. So multiply them all and add 1. What would happen? If you remember, there was one of the theorems that we proved, I think, in 2.3, maybe 2.4. I can check which one now. And divisibility of integers. It's 2.3. Every number greater than 1 has a prime factor. Da, 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 da. Sorry for this delay. Now we talking about 4 on divisibility of integers, yes. Yes, theorem 242 says any integer n greater than 1 is divisible by a prime number. So according to theorem 242, a being greater than 1, obviously, a has prime factor. Let me call it P. But remember, all the primes are here. So P cannot be someone else. P is one of those. So, since all the prime factors, all the prime numbers are in the list or on the list, P is one of them. Which one? I don't know. So P is equal to Pi, one of them, where I is between 1 and k, for some I, not for all, for some I between 1 and k, maybe P1, maybe P2, some Pi. So what happens basically? So A equals Pi times a certain number s, because A is divisible by Pi. But if we think of it in the terms of quotient remainder theorem, because plus 0, we can say that the remainder of A, when you divide it by Pi, I got 0. But then, if you look at this, Pi is one of those. I don't know which one. Here's Pi somewhere here. So if all the other numbers, I call that T, then from that equation, A looks like this. Pi is still there, times all the others, which is t plus 1. Because here is pi, some others, all the others I called t, and then plus 1. So what this says is that the remainder of A modulo pi is 1. That's A1. Here it says it's 0, here it says the 1, here's the contradiction. You cannot have the same remainder, the remainder 0 and remainder 1 modulo same pi prime number. Here's a contradiction. That contradiction then says what? The assumption that negation of p is true brought us to contradiction, so we conclude p is true, and that's our original statement. So there are infinitely many primes. By the way, for practical purpose, that's also important, because prime numbers are building blocks of integers, because every number is their product because of the prime factorization theorem. So it's very important that we have lots of material there, so that we are not limited by the size of that material. So that's why, for practical purposes, that's also important. All right, and now just I want to talk about contraposition now. Please don't mix them up, because here for contradiction we have the machinery, not p. You derive contradiction and say, and you know, stop and say no, then I can conclude p. Contraposition works the way we already discussed before. So p implies q is traded for not q implies not p. So you are actually treating two statements, so you don't reach any kind of contradiction. You are asked this, and sometimes you switch to this and say that's basically proving the same thing, if it's to your advantage. And of course, the main thing is here, when is it to your advantage? And let's illustrate how that works. Actually, here's a good example. You remember that statement from the first half where that I stayed left unproved. I used it somewhere, proving the square root of 2 is irrational, but I said, oh, that lemma actually stayed unproved. So, and I postponed it because I wanted to use it exactly here. So here is a lemma for integers. If m squared is even, then l is even itself. So when I look at this, by the way, contraposition you use only for if you have implication. So here it is, I'm supposed to prove this. And then I say the following, what is it that I don't like about it? Because I have information about m squared, and I should get information about m. That's a bad direction. Why? Because to go from m squared to m, you need to square root. The square root doesn't behave well algebraically, so that's not going to be good. I would rather go from simple, so basically I use it where I go from complicated to simple. Then I would rather go negation of simple into negation of complicated. It's always easier from simple to argue toward complicated than the other way around. There's a price to pay. I have to deal with this negation somehow. So this is ideal candidate. M squared is more complicated, so instead of that, I will trade it. That's what contraposition is. You are trading given statement for a different one, and you like it more, and the logic approves your method. So, contraposition. We prove that negation of e to m implies negation of e to m squared instead. So we kind of change the question, which sometimes is not legal, but here it is. So this is what we prove. And that's it. So we start. Assume that negation of e to the m, which means that m is not even. It is an integer. I'm writing here a little shorter than in the notes. Now what? Now we already have some knowledge from the first hour. Every integer is either even or odd. Once you know that it's not even, m must be odd. And then what? Now that's much better. I got rid of that negation. I have a positive information that means m equals 2k plus 1. Now I have equation, and now to go from m to m squared, that's much easier. I square things. Which is what? 4k squared plus 4k plus 1. And now what? Since I'm all interested even odd, I can factor 4, but I'll just factor 2. So it's 2 times 2k squared plus 2k plus 1. So if I call this s, and it is integer, and sometimes I see in your quizzes or in homework, you take some fractions and you give them names like being integers. No, this is product of integers and the sum, so this is integer, s in z. So it is 2s plus 1. So what is that telling us? That m squared is odd according to definition. Am I done? No, I'm not. Because showing that m squared is odd, I need to show that m squared is not even. But then I call that other theorem, first theorem of the day, that no number is at the same time even and odd. So if m squared is odd, then I can conclude that m squared is not even. Because no one is both even and odd. So I got not a even of m squared, and that's it. So Johnny, what I did once again, instead of proving the original statement, I proved this one, green one, switched, negation, started with negation of e to the n, finished with negation. So it's direct proof, it's not proof by contradiction, this is direct proof. I started with negation of e to the n, I arrived at the right side, so this is correct. And then because of principle of contraposition, this is equally valid as this. Once you prove this, this is automatically proved. And that illustrates the argument by contradiction. Let me see if there is something else here that I want to tell you. Oh yes, at this moment I might be going a little bit back and forth, but here is example 255. Example 255, and in that one it says prove that 5 plus 7 square root of 2 is irrational. And then as a remark, we can use the fact that square root of 2 is irrational. So if that's the case, how do we make a proof? Here it will be a little trick. So we all again argue by contradiction. Assume not P, this is P. So that means that 5 plus 7 root 2 is rational. So 5 plus 7 root 2 is quotient and that is not 0. And also I know that m is not 0, because if m was 0 this would be 0, but this is a positive number, so I also know, obviously I know that m is not 0. And here is now a very nice trick. I take a reciprocal of this number, 1 over 7 root 2 plus 5, and I know that that would be n over. By the way, that's why I needed that n is also not 0. And then I would rationalize denominator, multiply multiplying by 7 root 2 minus 5. So what would I get? 7 root 2 minus 5. Here I get difference of squares, so it would be 7 root 2 squared minus 5 squared equals that. What's this? 98 minus 25, that's 73. 7 root 2 minus 5 over 73 is n over n. Okay, you'll see in a moment where I'm going. 7 square root of 2. Alright, that made it a little more complicated. Sorry, I just noticed if I had something unpleasant here, it would be okay. Otherwise, I'll solve for square root of 2. There's an easier way to solve it. And I'll show you that later on. But this is also. So 7 square root of 2 minus 5 equals 73 n over n. So now what? I had two equations. And if I add them up, I'll get 5 will cancel out. Although I could get, we just got the 5 to the right side. It's not necessarily complicated, but this trick is useful in some homework problems. So if you add it up, this box and this box, you get the following: 14 root 2, 5 and 5 cancel each other out, equals m over n plus 73 n over n. Doesn't matter algebra here. Which is what? It's just a fraction. So this is, I can just simplify it and call it k over l. When I do fraction, I don't know, common denominator. But from here we would get root 2 equals k over 14l. That would mean square root of 2 would be rational. Because I have two integers, which is contradiction. This idea with the reciprocal is powerful for some other more complicated situations, but actually another proof. Much simpler actually. I just used too heavy machinery for this simple problem. What would that be? I could have done it like this. I could have done it just solving for root 2. 7 root 2 equals m over n minus 5. When you make common denominator, you get n minus 5n over n. So here root 2 is n minus 5n over 7. This is integer, and this is integer, not 0. Quotient of two integers is integer, so 1 over 2 is rational. Contradiction. So this contradiction says that our assumption, not p, was wrong because it brought us to something that we know is wrong, because square root 2 is irrational. We already have theorem proving that or confirming that, and then so this is contradiction. So our assumption was wrong. 5 plus 7 root 2 cannot be rational. It is irrational.